Hey, welcome. In this video, we're going to go through an exercise of talking about everything you need to know to scale a web app from a few users to millions of users. This is likely a pretty common system design interview question, but it's also a good thing to understand if you're building out your own apps. So if you're going to end up being a backend engineer, or if you are a software architect, these are the kinds of things you're going to want to understand. And we'll start with just the smallest little tiny app that might have a few users, nothing too crazy. I mean, look at it. It's so cute. It's not going to be able to support millions of users though. So we're going to continue to add new things to improve the overall capacity of our app so we can support more and more users. Before we get started, a few things I wanted to mention. First off, the System Design Interview book, pretty good book if you want some practical exercises on system design. So I've been reading through this. Might be a good additional resource for those of you who are looking to do system design interviews. The next thing is I have a backend engineer's mind map, and this is going to categorize a substantial number of different softwares and technologies, so you have a good framework for learning, as well as a roadmap at the bottom giving you a step-by-step guide on which technologies to learn in which order. Now, if you're learning the things to become a software engineer, but you need some additional support, I have a mentorship program where you can get one-on-one support and accountability to help you learn all of the different components of building backend services and websites. Perhaps you're already in tech and you're looking to advance your career, or you want to transition into your first software engineering role. Whatever it might be, that mentorship program can help you get there. So I'll have a link to that in the mind map down below. So we've talked about scalability a little bit in the previous system design videos, but it's not really a prerequisite to watch this video. So if you're just jumping in, that's fine. But we're going to review real quickly what scalability is. In general, scalability is the ability to support more users. So if your app grows, your app doesn't collapse because you've hit maximum capacity. So pretend this is your web server, and you might be utilizing, say, 50% of the server, maybe even a little bit more. But as you start to consume all of the resources of this server, you might have some issues. So you definitely don't want to get too close to using all of the computer's resources. Now that exact number, whether you utilize 50% or 70%, that really depends on how much variation in the computation is needed. So if you're at a constant 70% all the time, that's probably fine. But the reality is typically the usage will go up and down. And that usage can vary on time of day or a certain season. So you might typically say only be using 60% of the total computation power of the server. But let's say your application is a little bit more popular on the weekends, and now you start getting up here where you're at 90%. Well, now you have to really start considering how can we scale so we can support more users. So you'll need to concern yourself about scalability from ups and downs, but also the growth of the app over time. Perhaps when you start out, you might be right here in terms of the growth of your application and your business. So this might potentially work, but next year you might have twice the number of users. So not only do you have to think about the ups and downs, either day to day, week by week, season by season, but also the growth over time. So that's the idea of scalability. We need to structure the backend to be able to support more users. If you're dealing with just day-to-day ups and downs, then you need to think about having enough capacity to support the changes in traffic. And this can often be as simple as getting a stronger server or adding more servers. But when you start thinking about growth over time, you might need to introduce some different systems or structures to your backend to make it more reasonable. So we'll talk about both of those things in this video. So let's make sure we are on the same page with vertical and horizontal scaling. So I have a video that should be coming out soon, which will talk about the ups and downs of these in much more detail. But as a general idea, vertical scaling is improving the power of a single system, often called scaling up, where horizontal scaling is just adding more servers. So a visual difference would be going from this to this, and now I have a much beefier system that we can support more users with. Comparing that to just going from this to now, say, 3 smaller nodes. So both of these can achieve similar results. It's just a matter of which one you want to do. And most likely it's going to be a combination of both. But throughout this, you'll need to understand that it's often the case we can be working with multiple servers that are working together as a single unit. That's really important to understand because one of the easiest ways to increase the scale of our app is just to add more servers. But you'll have to set up your backend in such a way that this can work, such as using a load balancer. And the ease of doing this really depends on the type of thing you're trying to scale. So doing this is a lot easier with a stateless backend API, for example, but more complicated to do with a database. Now, it's often the case you can also have some automation. So we'll just say auto scaling. And this addresses the first thing we were talking about, which is the ups and downs in usage from day to day or week to week. The simple solution for this is an auto scaling setup, where if you have more users come in, you just add another node, and I didn't draw it good here with room, but you can add more nodes to support those users as needed. Then when the ups are over, you no longer need that additional computing power. You can remove those nodes and go back to your standard 3. While people often use 3, you don't have to use 3. So don't think there's any magical number here in terms of the number of nodes that you use when you're using horizontal scaling. For our visuals here though, I'll often draw it as 3 nodes. Now a node is just another name for a server, so you probably got that figured out by now. But as we add nodes, it basically just means adding a server to a larger cluster or unit. So auto scaling is a term to describe elasticity, and this is a little bit different than scalability, which this deals with the growth of users, being able to support them, whereas elasticity refers to going up and down in computer hardware to be able to dynamically adjust. All right, so we understand the types of scaling. Now there's one additional thing I want to talk about, and that is a typical app structure. So we'll go through that architecture real quick, and then we'll go through the exercise of starting with a few users and going to millions. So an app architecture could depend a lot on the type of app you're building. For this exercise, I'm really thinking of a web application or even like a mobile application with a backend API and a database. So this is the typical 3-tier architecture, which we did a dedicated video on, but that's what we're going to be going through in this video as well. So I won't get into all of the details of this because it's not really the point of the video, but the general structure will look like this. You'll have a database layer, then you'll have a backend layer, and then you have a front end layer. This front end could be a website, it could be a desktop application, it could be a mobile application, it could be a video game. It doesn't really matter. The main thing you need to understand is that it connects to some centralized backend, which is our job to design, and a database to store information. This is the basic structure, and then we'll kind of adapt this as we go. I wanted to draw these out separately at first. So we have the DB, we have the back end, and we have the front end, because the way you scale these might differ. So the database scaling, I'm going to have a different approach than the back end scaling. And same idea, the front end might be a little bit different as well. So we'll go through some of those differences throughout this video, but we'll primarily be focusing first on this back end, as there's a lot of things that we can do to make this back end better, and scaling a database is more complex. There's a lot of things we can do at this level to reduce the computation at the database level. So by working here first, we can simplify this. So a very simple example of what I mean there would be a caching layer. We can cache data so we don't have to access the database as much. So that's just an example. We'll get into the details of what that means. And now with all of that foundation out of the way, we should be able to get started by going back to our little tiny square box and scaling from a few users to millions. So let's start with a single server. I'm gonna make it just a little bit bigger than what we started with, so I have some room to draw in here. With this structure, we're going to have the database, the backend, and the front end all served from a single server. So this would be the most simple architecture, but it's also going to be the most limited. So within the server, we have a database server. So basically the database is in the same computer. This would be kind of like if you're on your local computer and you download Postgres or some database. You can run your backend from that computer and you can connect to the database that's also on that same computer. In this environment, we would also be hosting the web server, so we will have something like Nginx or Apache, which will allow us to take requests and process those requests on the backend, getting the data from the database, and ultimately giving HTML or CSS or whatever the front end is to the client. So it will look something like this. Let's say the client is over here and they're accessing from a computer. Let's just say we're building a website. They make a request to our server. We have a single application in code, which is going to probably have some ORM or database models to work with the database. It will probably have some API, so we'll just say the backend, and it probably has some way to generate the front end. So with it being just a single monolithic application, you might be using some template engine such as Jinja 2, Razor, Pug. There's a bunch of different template engines, and basically what those will do is they will allow you to take some backend code, let's say it's Python, give you an HTML structure, and you can write that Python in the HTML. It will process it on the back end, ultimately giving you out just HTML, which can then be sent to the client. So we're kind of getting into the weeds here of how to actually design the code, which I don't want to get too distracted from scaling apps. But with this structure, everything is being done within a single application. We've talked about the MVC design pattern, and that might be something you implement for this monolithic application where the request from the user hits a controller. That model will do the database stuff, getting data from the database. We'll embed it in that view, which is this templating stuff. And then that is the response that ultimately makes it back to the end user. So you can kind of ignore all of the details here. The main thing you need to understand is that we are running from a single computer, and that's very limiting for a couple of reasons. So let's talk about the pros and cons of this setup. The pros, it's super simple for beginners. If you're working on your first web app, you can do this in no time. Additionally, it is simple to scale. Now, I don't really want to say that it's easy because there are some complexities, but it's simple because all you have to do is add computer hardware. The limitation is you can't be specific about what parts of the app you want to scale. So it's simple to scale because all you would do is vertically scale. If you need more RAM, you just add more RAM to the server. If you need more CPU, you just add CPU to the server. But this is directly related to the con, which is you cannot scale sections independently. Second major con is there is no separation of concerns. And this is actually focusing more at the code level. Everything is just in one app on one server, meaning everything's tightly coupled. It's going to be hard to work on that application with a larger team. So if it's just you, hey, maybe this will work. But as you start to add new members, it's going to be more challenging to scale not just the actual computer hardware, but actually build code that's easy to work with in a team environment. So you may be limited to just the general scalability of the code and the maintenance of that code. So that might not be a direct performance concern, but it is a concern in terms of going from where you are now to millions and millions of users. If you're doing that all within just a single project, it might be difficult to achieve the end result of having millions of users if you have a limitation in the code maintainability and you cannot easily add code or keep it organized working in a team environment. Next major con is this is a single point of failure. You have one server. If something goes wrong with that server, literally everything is broken. So this is the biggest red flag in my book here. You don't want to have a single point of failure, and having everything on one server is asking for problems. There's also concerns such as DDoSing. So if somebody wanted to get your app to stop working, they could just send a ton of traffic to this one server, maxing out its resources and causing your app to crash. The other thing is this is limited to vertical scaling, which likely has diminishing returns as you go to a larger and larger system. So we want to think of ways we can introduce horizontal scaling to this setup. So this would be the pros and cons of this scenario, which is the most extreme example of a monolithic application. Probably not something you're going to be doing in the real world as a professional developer, but if you just have a small project of your own that really doesn't have a lot of users, this architecture definitely could work. It's the simplest. You just need to set up one virtual machine on the cloud. You can run everything from that VM and you're good to go. But if you need any kinds of reliability, failover, or scale, you're going to immediately hit all of these problems. So we're going to talk about the next logical move, which is to go to that 3-tier architecture, where we split out the database, the backend, and the front end. So now with the 3-tier architecture, we're going to have a dedicated server for the database. So you can think of our database inside of this computer. That looks really terrible. I'm gonna have to redraw that. So now we have a dedicated database server. We have a dedicated server for the backend, and we can have, if needed, a dedicated server for the front end. This split wouldn't necessarily be required, but it's a very logical split, and it allows us to independently scale. So going from that previous all-in-one monolithic thing, I would probably just jump to this 3-tier architecture and just split it out to have the back end, the front end, and the database. I would also split it out this way just because of my experience with cloud infrastructure. Very easy to do this. So for example, in AWS, it might look like this. We have RDS, EC2, and then S3 for our front-end static file hosting. The exact technologies you use for cloud providers might vary if you're going to Azure or Google Cloud Platform. And if you're self-hosting, it's going to be a little bit different, but these are the things I'm familiar with, and doing it in this structure is very easy, where you have a dedicated front-end application using something like React or another front-end library. So we're no longer using the template engines embedded in the backend. One way to achieve scale easily is to use serverless services. So in this scenario, you pay a cloud provider for the usage of your application instead of for a certain size of server. So that's pretty common with the front end. So going back to what I just had with S3, it is a serverless thing where you don't have to provision, a medium server with this much RAM and this much CPU. You just host stuff on S3 and get charged for doing so. So the easiest next step would be to make this a serverless thing. And we're just going to jump right to that. So running the front end from some serverless service is going to be the ideal setup since you're just working with static files. It's very cheap, very simple, and you don't have to be serving those from the back end. They would just have HTML, CSS, and JavaScript, and that JavaScript would then make a request to your backend API. So that's going to be your typical architecture. The exact details of how you host the front end is not a huge concern because this is most likely not going to be the bottleneck. Since you're just working with static files, you're not doing any computation. There is computation being done in JavaScript, but that's all done client side. So that's given to the user and the JavaScript will execute on their machine. Our biggest concern is probably going to be here where we have to do computation. And doing computation for each request and doing that for potentially millions of users can get pretty expensive. So we're going to prioritize scaling this layer first. We're not even going to worry about this layer, and then we're going to look at that layer later. So let's just kind of zoom in on this section and talk about things we can add or change to make it better. Before we go in and change a bunch of stuff with our backend architecture, let's just do a quick check-in. So this would be the next logical step, going from just a monolith to now having this 3-tier architecture with basically 3 sections. And you can now scale each one of these independently. So if your original bottleneck was just the entire server, it might have been a little bit more challenging because you'd have to go in there and figure out what's using what resources. But now, if you have a dedicated database server, you can just see how much resources is on that server and is it enough to run that database server. So you can independently scale up or down. Same thing for the back end and the front end. So that is the biggest upgrade here, is independently scaling these things. Having these split out to independently scale can potentially help us find any bottlenecks and just improve the overall performance of our application. So let's talk about the pros and cons of this setup. The first one, it's really common, which means you're not doing some crazy setup nobody's done before. If you run into issues, you'll probably be able to find plenty of articles or people to support you to get those issues figured out. Next up, we can independently scale the different sections, which is a major improvement over the previous architecture where everything was ran from a single server. The cons: from a code perspective, you will now have to have an API, whereas before you were possibly just using some kind of template engine. You didn't have to design your API layer. So I don't even know if that's a con. It's just something to be aware of. Perhaps you now have to code more interfaces between different components. It also adds complexity with cores, so cross-origin requests from the front end to the back end. You'll have to figure that all out, as well as networking between the back end and the database. So you have to learn a little bit about permissions and how to actually get those to communicate. Now, when it comes to scaling, you can be more granular, growing each individual thing up or down, but you have to be able to know how to identify what parts aren't working well, and you can't just grow one server, which is really simple. And we're still limited to vertical scaling in this setup, with the exception of the front end, which is probably serverless, but we're really thinking about the back end here. We didn't talk about how to actually set up horizontal scaling, and that's going to be our next logical progression. So overall, this is better than the first setup, but still has some limitations. All right, so we've made it through the extreme monolith, the 3-tier architecture, and now we're going to zoom into the back-end layer of that 3-tier architecture and talk about scaling the back end. Most likely this is going to be the first bottleneck you encounter because the front end is extremely easy to scale, and the database layer you'll most likely just vertically scale for a while. So we'll zoom into that back-end layer, and the very first thing we're going to want to do is do horizontal scaling. This is going to allow us to remove the single point of failure. If you have just one backend server and all of the requests go to this same server, and for some reason this server goes down, your entire application is now broken. So if we introduce horizontal scaling, we'll now have multiple servers, which means we have some redundancy. If one server goes down, we can redirect traffic to a server that is working. So we can just introduce a couple of additional servers. These don't have to be more powerful servers. Simply by adding more, you can achieve more throughput. So we've pretty much 3x'd the number of users we can support. And if for some reason one of these goes down, we can just redirect this traffic to another node instead of this one. So all in all, our system is still operational. So far, so good. The challenge is, how do you know which of these servers to connect to, and how do you do that from a front-end application if you have multiple endpoints? And what if one of them goes down? Well, this is all going to be done for you by a load balancing layer. So you can think of the load balancer as a service which will take requests and direct them to the correct location. So it might look like this, where blue is a request, and then this will direct that to the appropriate server. So we only have one endpoint, and this would be where the front end connects to. All of this splitting out the traffic to the individual servers is going to be abstracted away from the front end, handled all by the load balancer. So the load balancer would be the one responsible to adjust the traffic if one of these servers goes down. So it might look something like this. And the load balancer will also do its best to balance the traffic. So instead of this server just getting double the traffic, it would now just split 50-50 across these two nodes. So that's what a load balancer does. And when I draw these out, I'll often just draw it as like a circle or a square around the servers. So it might look something like this, where we have the 3 servers and they're all wrapped by a load balancer. So now this is what our backend would look like, where this would be the front end and that would be the database. And you can imagine having a domain such as api.mysite.com, and this is going to point to the IP address of that load balancer. So far so good. Let's go through the pros and cons of this. So for the pros, we removed the single point of failure in our backend. We're able to achieve high availability because we have failover. If one server goes down, the traffic's redirected to another server, so the overall functionality of our application is not disrupted. We are able to horizontally scale, which in theory is cheaper than vertically scaling due to diminished returns of vertical scaling. Plus, APIs are typically stateless. They don't have to store any information like a database. So there's no major downside to using horizontal scaling over vertical scaling. Another pro is that this would support auto scaling, so we can increase and decrease computing hardware as needed for different spikes in our traffic. Cons is you have to add a load balancing service. Not a huge deal, but you have to be aware of that and know how to do that. And then I would say the other major con is no caching. So every request is seen as a fresh request coming from the front end client, hitting the API, making a request to the database, then returning that ultimately back to the client. Even if 80% of the requests are the same thing, it's still seen as a completely new request every time. So the next logical move will be to talk about things we can do to cache information. You can think of a cache as something that stores information temporarily. So say we have a database here, and this database has some data. Let's just put some numbers. And then we have a cache layer here. And then we have a client make a request. And the request is to retrieve the value 5. So 5 is going to be stored in the cache. And then the next time a client makes a request to get 5, it just retrieves the cached 5, not having to make another request to the database. So you can see there's only one request to the database, but 2 clients requesting 5. So this means we can drastically reduce the amount of requests to the database using that cache layer. Say a client requests something that's not in the cache, say it wants 7. It would basically look in the cache, realize it's not there, retrieve it from the database, and then that would be stored in the cache as well. And then 7 would be given back to this client. So that first client might take a little bit extra time because it has to go to the database. But then for future requests, say this client wants 7 as well, it's going to be a lot faster because it can just grab the cached version. So that's the idea of a cache. There's also another related thing, which is a CDN. And this is a content delivery network, but it functions pretty much like a cache. So say you are over here and you want to make a request to my server down here. The amount of distance you have to travel is quite far, and when you make a request to some web server, that request ultimately does have to make its way through the internet and travel some distance. So that's a far distance to travel, and that's going to make the application slower. So what a CDN will do is it will basically put your application's cached results in a bunch of different locations. So it might look something like this. And now when you make a request to get some information from the server, the request will actually go to the closest node to you, drastically reducing the time it takes to get the response because you don't have to go all the way back to the main server. So a CDN is going to introduce two major benefits. The first is it's going to be an increase in speed for the end user, or you can think of it as reducing latency, and it's going to reduce computational effort on the end server because that request does not have to make it to the server. So introducing a CDN to our structure is going to be the next logical step. Now, what people typically use CDNs for is for caching static content, CSS, HTML, JavaScript, pictures, videos, and this is ultimately to increase the speed of the application so the end user's experience is much better. While you can potentially cache certain API responses that don't change very frequently, you're most likely going to use CDNs for this purpose and use a separate caching layer such as Redis to improve the compute aspect of the backend. That being said, if you are trying to build an app that millions of people are going to use, you will definitely want it to be fast and performant. And one of the best ways to do that is to get the files as close to the user as possible. So one of the most popular CDNs is Cloudflare, and you could add that to your overall architecture. So let's go through the pros and cons of a CDN. The biggest pro is going to be a reduction in latency. So from the time the user requests your web page to when it receives a response, it's going to be much faster with the CDN. The biggest con is it increases the complexity because now you have to know how a CDN works. You have to worry about the cache time. So for example, if data does change, how long until that cache expires and the new static files are pulled for the CDN, or you have to go in there and manually expire stuff. So there's a lot of complexities introduced with caching layers. So under complexities, we could have the time to live, which is the cache time we were just referring to. You also have to worry about things like cache hit ratios. Freaking fly. It's terrorizing me. This one goes back to the TTL, but you have a risk of serving outdated data. This is also the easiest way to bring an app global, pretty similar to latency, but if you zoom in on that idea a little bit, you could have servers in different continents, or you can cheat and just use a CDN to kind of make your app global. Not the perfect solution, especially if you have to make requests to the backend and the backend is in a different continent, but this is a great first step because it's relatively simple to set up, it's affordable, and it will reduce latency for users significantly. It can improve security. So often CDNs have things like DDoS protection and other services to protect your app. And if set up correctly, CDNs could be good for SEO. So you can read more about that if you're into SEO, but just something that might be worth knowing about. The other one is it's great for images, videos, downloads. If your app utilizes a lot of images, videos, and downloads, you may benefit from a CDN, not only for performance, but also for cost savings. So you may need to look into that in more detail, but worth knowing that this exists. If you are building something like this, you can do some additional research into CDNs. So here is the flow of a request from an end user's computer. They're going to make a request to our front end. Now when they do this, they'll just put in a URL into their browser. This is going to utilize a DNS record. So this is kind of a separate thing, but just kind of wanted to mention it here. And that DNS record is going to associate that URL to some IP address, typically the IP address of the front-end application that they're trying to access. When you're utilizing a CDN, it might be a little bit more complicated because it might direct them to the IP address of an edge node instead of directly to our front-end server. So I'll just write the CDN here. So they'll either get the front end from one of the edge nodes or directly from the server. And that'll make a request to the load balancer, which is going to manage our backend. And in here we might have, say, 3 servers, and it will manage the traffic between those. And then I'll just say backend here. So it might look something like that. I mean, you can visualize it however you need, but basically the load balancer manages the 3 backend servers in this scenario. And we just have a single endpoint for the front end to connect to the backend. And then each of these will connect to the same database server. So it looks something like that. So far, so good. Now, the next thing that we can introduce is a caching layer, which instead of caching here, will cache here. And this can reduce the number of requests to the database because we might be retrieving the same stuff over and over and over again. So we get to store it in this cache layer in memory, which will increase the overall speed, but also reduce the computation needed at the database level. So as mentioned, the next thing you can do to improve both the performance and the scale of your system is to add in caching between the API backend server and the database. So it might look something like this, where you have the database, and then you have a cache layer, and this will act as an intermediary between the server and the database. So a request to the database will first check the cache for that value. So the biggest cache that you're probably going to come across is Redis. There's also Memcached and probably some others, but this is an in-memory thing. So this will be in RAM. But you don't need a lot of RAM to cache the majority of requests. It's often the case that there is some natural data that gets retrieved a lot more frequently than other data. So it might be the case that 80% of the requests are retrieving 20% of the data. So in that situation, we could put the 20% in RAM, which is substantially faster, and reduce the total of request counts to the database by 80%. So not only do you get a lot more speed, but you massively reduce the amount of computing power that the database layer needs. Now, we talked about how caches work. We said that when some value is retrieved from the database, the first time it will pass through the cache, grab the data, and then on the way back, store that data in the cache. The other thing you need to be aware of is if you update this data, let's say we updated it to a 6, we would need to write our application code so that when we make that update, we also update the cache or clear the cache so that the cache doesn't have outdated data. So again, an extra complexity you need to be concerned with. That's an easy way of doing it, is just whenever you update the data in the database, also update the cache or clear the cache. Otherwise, there could be out-of-sync data here, which in some applications, that's not a huge deal, especially if the time that the data stays in the cache is not forever, right? If it expires every so often, then this will basically just lag behind the database a little bit, but just updating both at once is a really good way to keep those in sync. Now, an in-memory cache does store data, but it's all volatile because it's in RAM, meaning if the system shuts down and comes back online, the data is going to be gone. It's not stored on disk. That's usually fine because we can just get the data from the database again. It would just be a temporary performance hit because nobody would be hitting the cached data. They would have to make the request to the database. You can scale the cache horizontally and have less of concerns with data issues, but you can look into all of the details on Redis clustering and the different configurations you can do. But I would horizontally scale the cache before I horizontally scaled the database layer, unless you're working with a database that is very good at horizontal scaling, which we'll talk about here in just a moment after we get through the cache section. But you can scale this cache as needed to support the number of requests from the API. So this does add an additional layer, and you might think, oh, that would cost more. But based on the way the cache works, it's probably going to end up being cheaper and substantially faster to use a cache versus just making a request straight to the database every time. And you can also really consider situations where perhaps there are some complex joins or some things going on behind the scenes for a particular query, and caching the result of that is going to save a lot of computation, because you're not going to have to make those complex joins over and over again. So let's talk about the pros and cons. The pros, it is going to reduce the amount of compute needed for the database. It's going to improve the overall speed of your application or reduce latency. It's probably going to end up being cheaper. The major cons is an increase in complexity. So all of the issues that we were talking about with the CDN is going to apply here, but it's worse because it actually requires us to do different stuff in our code, such as write to the cache or read from the cache. If we update something in the database, we might need to update the cache or clear the cache. All of this stuff has to be done in code, where the CDN is a bit more automatic. So it's going to increase the development efforts, which could actually cost money, because if you're paying for development time and they have to write more code or the system is more confusing or complex, that's going to take more time. That's a pretty good summary of the pros and cons of a caching layer. And now let's talk about the database layer. Up until this point, you've done a lot of things to scale your app, and you're probably in a good scenario. You usually don't have to do too much with the database beyond vertical scaling, basically just creating a really big database server, but you might be concerned about the high availability aspect, and for that you can have a stand-in database. So if this is your database server, you can have one that is just there in the background as a backup if something goes wrong with your main database. That is one option as an alternative to having multi-master clustering, which can be fairly complex. You can also clone to read nodes, and I'm kind of glossing over a lot of the details here because I'm going to have multiple videos on database systems coming up. So I would just encourage you to check those videos out for more details, but I just wanted to include the basics here to comprehensively cover scaling an app. These could be read nodes, and it's often the case that an application is going to do primarily reads, so you might do just one big write or master node server, and then have a bunch of independent databases that are for reading, so you can scale reads and writes independently, and probably scale reads higher than the writes because you probably have more reads than writes. This may be the setup you use if you're using a relational database hosted in RDS, for example, but you can also use larger cluster services for relational databases, and you can also look into multi-master databases, especially if you go into the NoSQL world. That's pretty common, but typically that previous setup is adequate. However, if you do get into multi-master, it might be something like this, where you have multiple nodes, and the data is either split up across these nodes or replicated to each other. So there's various setups for clustered databases. Again, we're going to get into that in more detail in upcoming videos. So to summarize the database layer, I would pretty much just scale vertically as much as humanly possible before having to scale horizontally, unless you're working with a database service that does scale horizontally very nicely. And then as for high availability, you could have a synchronized stand-in node, which could fill in if the main server goes down. That's just one approach. There are probably many different approaches to the data layer, but most of the time, the issues are going to be at the API level, the caching level, or even the CDN, static content, and front-end level. Another thing you can do with the database layer is instead of storing everything in one massive database, you could split that out into smaller, more focused databases. So for example, you might have a database just for user authentication. Same idea with the backend. You can split out your services into smaller, more focused services and start moving towards a microservice approach, which you can then more independently scale. It does always introduce complexities because you'll have to worry about communication between the microservices. But as a general rule of thumb, if a service starts to get too many users, you can split it out horizontally or grow vertically, or split the service into smaller microservices and scale those independently. Sort of how we did that from a monolith to a 3-tier. You could do the same idea, just more granular. So let me just do a quick overview of what our full architecture will be. Kind of something like this. So we have the end user making a request, and this will get the front end or some cached version from the CDN. This will make a request to the load balancer, which will hit the API servers. And then you don't really go through a cache to get to the database. It's more kind of like this, where we have the cache and then we have the database. Because you can think of the cache as a data store, kind of like a database. It's just that it uses memory instead of the disk. So in code, you would check the cache, and then you would go to the database if it wasn't found. So there's a million different ways of visualizing it, so apologies if I'm changing it, but I don't want to give you the impression that there's only one visual correct way of representing this information. I also forgot an E, so there we go. So that is an overview of scaling an app. We're going to cover a lot more system design topics and get into some of the information we talked about here in much more detail. So stay tuned for those upcoming lessons. Again, as a reminder, if you want the backend mind map or you're looking for more involved mentorship, check out the links down below. That'll get you started to get into a software engineering role and get some more practical guidance on things like this. So stay tuned for upcoming content. I'll see you in the next one.